Welcome everyone. Today I will introduce you another one, process one. Yes, we are writing a new process one for OpenEuler, and it is written with Rust. Okay, its name is sysMaster, and we open sourced at OpenEuler. OpenEuler is the new OS platform. We already open source it at Git and GitHub. Okay, it's currently incubating at OpenAtom. Okay, right. So today I will go with these three paths. First, why we want to write a new process one, and second, what it should be, what it should like, and how we'll decide and its architecture. Before that, what is the process one? Process one, actually, in our Linux OS, there is the process called process tree. Okay, it's like the tree. So the first process, that's process one, is the root of a tree. So it's the first user space process in Linux, and all the other process are its ancestor. It has two main roles. First one is brings up the whole system. Second one reads the other soon-be processes. So in a process tree, its stability is very important. That means it affects the whole reliability of the Linux OS. Oh, but before that, we already have many process one in the whole operating system world. Okay, currently we have counted there are more than 20 process one. In very different OS distribution, we have such as systemd, upstart, sysUnit, and loT. Normally in Red Hat OpenSUSE, we use systemd, Ubuntu, Debian, we use upstart, okay, and we found that there's some difference, and we also talked about that in different US, we have different process one, which means that this is because the demands or what this OS we want that demands on the process one, what it looks like. So before that, we talk about OpenEuler. And OpenEuler, we are trying to build one OS for versatile scenarios, includes cloud servers, edge, embedded devices. Or we have to analyze all these scenarios. The first one, in traditional servers, according to our statistics of our maintenance and SRE team, we found that we have a table here. For the last 5 years, we have many bugs in process one. Okay, it accounts for 16%, and these bugs stands long for the past years. It's still high every year. And the third one, nearly 1/3 of bugs are memory-related bugs. Okay, that's really harmful to the maintenance team. Okay, and as we said before, its reliability is very important to the OS. Once it has any bugs, to need to recovery or need to restart process one, it causes the whole OS to restart. Okay? It is very critical. So we need this process one as reliability and has an ability to self-recover. That's the traditional servers. And second, in cloud native, in our current world, especially many of our virtual machines applications are just managed by Kubernetes or OpenStack, which means in in the perspective of our SRE, they have to handle many different management platforms. But Kubernetes and OpenStack, they cannot manage those system services in the OS, which means we're trying to provide another agent in the OS in OpenEULA to connect to the Kubernetes and OpenStack for easy maintenance. And the second one, currently in the container world, many of us, we are building the container OS like Firecracker or such as. And in this container world, most of apps are containerized. So we don't need a huge process run anymore. We hold this in this container OS. The process run is as small as possible. So we want this process run is part of Kubernetes or OpenStack ecosystem and reliable, small and reliable. Embedded system, embedded devices. The traditional process run is huge to use in an embedded system. And the normal process run in embedded system, they don't have a service management to manage those system service. So we want this process run is lightweight, small, and have the ability of service management. That's all our scenarios. So we want this sysMaster is ultra lightweight, highly reliable, and one process run can cover for versatile scenarios of OpenEULA. Okay, and then it has the full monitoring and self-recovery mechanism for its reliability. That's our vision. Before we were trying to write our first code, we decided that which programming language we were using, C, C++, Golang, or Rust. And last we choose Rust. I think the first thing is it's really growing fast. And it is also emerging in our fundamental software. It is also accepted by Linux kernel last year. Okay, and that's the first thing. It's very famous and popular. And the second thing, Rust, it is features for security and high performance. That is what our sysMaster wants. So we choose Rust for our programming. Next is our design. We talked about it before. In sysMaster, we hold it is ultra lightweight, small, reliable. So we decided as 1 + 1 and plus n. The first one is init. It is the real process one. It is as simplified with only kloc. And the second one is core. Only provides the core functions of service management and self-recovery. It should support live update and hot restart, and don't affect the running of OS. And the other key system functions will be plugged by the other models, and they can easily combine with those one and one. This is like Lego. In Chinese, we call it 榫卯. These two Chinese words. Okay, and this is after our design. And the first one, it's init. It is the real process one. It needs to read zombie process, brings out the whole system, and also monitoring is sysMaster core. It is also, currently it is only less than 1,000 lines of code. When it is running, the whole code is only 400 lines. It is suitable for the embedded devices, and it is really maybe really reliable. Currently, it is down. And second, the core, sysMaster core. It provides the important self-recovery mechanism and also the service management for those system service. It is added a reliable framework. It currently supports the hot restart and live restart, live update to improve those reliability. And we decided in two cases. The first one cases is once it is running to handle the daily routine when it crashes, and then it self-recovers. And the second scenario is it is trying to call or to bring up the other apps. At that time, itself or still crashes, and then it tries to self-recover. We have done it, and all this during this period, the whole OS and services are running properly. We have a small demo here. We can show you later. Okay. Next, its extensions. As we said before, it has a design as 1 plus 1 and plus n. Yep. And we introduced it, the init, the core, and the other all key functions will combine with this extends. And those important system functions, we call it is consists as loGao. Okay. Currently, we have finished the dev master. This device master will provide this function as device manager, and currently it is working. We are building out it. And in the near future, we will bring out the bus master and unit master for other kind of system functions. Okay, a small demo. Yep, no. Yep. Here, is my colleague, and he's trying to show. He has many. He's using the process one, the sysMaster running. Oh no, now it's. Oh, I'm going back. At first, it is running it within a container, a systemd container. Within the container, there's a systemd trying to bring out many system service in the container. Then it runs it starts a server at this window and trying to start up the systemd service here. Okay. Yep. And start up it. It is running. It's systemd, and okay, try to bring up the service, and then we will see that there's receiving requests. Then you try to set a signal ball, a signal 6 to this function, and then it stops. Okay, and this is so with systemd that this service is queued by signal 6 signal ball, and then we can self-recovery. So next, we'll try with sysMaster. Then you can see that sysMaster will try to self-recovery. Okay. Yep. Learning with sysMaster now. Try to bring out the test service. Yep. Ping again. Okay. Try to kill you again. There's something wrong, but it's still running. Yep. It's working fine in the system container. Okay. That's my show for today. Okay. Thank you.